Okay, continuing in the kinetics unit, we're going to talk about reaction mechanisms. Reaction mechanisms explain that reactions can occur by more than one step, and then if it does occur in more than one step, then the slowest step determines the rate of the reaction, kind of like the weakest link in a chain. Okay, and we hope that after this unit you can describe the relationship between the reaction mechanism, the order of the reaction, and the rate determining step. Okay. The sequence of events that describes the actual process by which reactants become products is called the reaction mechanism. And what it is the series of, say, smaller reactions that occur. Up until this point, we've pretty much have written and approached chemical reactions of things that happen in one step. Most often there is an underlying mechanism, a series of steps that actually occurs that is represented by kind of the overall chemical equation that we see. Sometimes they occur all at once. Sometimes it's through several discrete steps. For each of those discrete steps, and make sure that you understand that it's these discrete steps, each of these discrete steps is known as an elementary reaction or an elementary process. So when you hear the term elementary reaction, you can assume that that happens in one step as written. Okay. When you're talking about reactions, you talk about something called their molecularity. And you'll see when I'm talking about mechanisms, I tend to use examples and explain terms as we go along. So make sure that you get these definitions of these terms down. Okay. So when we're talking about molecularity, we're literally talking about the number of molecules that show up as reactions in these elementary reactions. Unimolecular, I've got one molecule as a reactant. Bi, I have two. And then ter, hopefully you can see that that's going to have three molecules as reactants. The cool thing about elementary reactions is you can write the rate laws straight from the reaction as written. So if it's a unimolecular, A, component or compound A is going to make products, the rate law is the rate constant times A, concentration of A to the first power. If it's A plus A or 2A, this coefficient I can use as the power in my rate law. Okay, so A plus B, rate law is K times the concentration of A times the concentration of B. We can do this because these are elementary steps. Prior to this reaction mechanism discussion, we had to have experimental data. Now if you're told that it's an elementary process or reaction, you can write the rate law straight from the equation. At this problem, it's been proposed that the conversion of ozone into O2 proceeds by a two-step mechanism. Describe the molecularity of each elementary reaction in the mechanism. Write the equation for the overall reaction and identify the immediates. All right, so if we look at the molecularity for this first reaction, I see there's one molecule, so this is unimolecular. For the second equation, I have two molecules of reaction, so it is bimolecular. Right. Write the equation for the overall reaction. Well, O and O appear on either side, so now I have 2O3 gas phase reacting to form 3 oxygen molecules. That's an O. Okay, very similar to Hess's if you remember. Identify the intermediates. Intermediates are going to be things that are produced in a reaction and then used up in a following reaction. So the intermediate for this is going to be the oxygen atom. Okay, make sure that you understand what intermediate is. All right, looking at another problem, we have this reaction. Proposed mechanism, two-stepped. Okay, it asks, is the proposed mechanism consistent with the equation for the overall reaction? Well, how do we determine that? Well, let's add them up. This and this will cancel. So I'm going to be left with this. If you want to name them, you go right ahead. Goes to CH3. Is this equation the same as the original? Yes. So is the proposed mechanism consistent? Yes. What's the molecularity? Again, this one will be unimolecular. This one with the two molecules will be bimolecular. The intermediate will be the molybdenum with 5 carbon monoxides attached to it. Okay? So, following reaction occurs in a single elementary reaction. Predict its rate law. Remember, I'm told here that it is a single, here we go, that it is a single elementary reaction. So I would predict that the rate law is K times the concentration of H2 times the concentration of Br2. I think this is actually what the rate law is, which tells me that this is perhaps not a single elementary reaction. Okay, so if we consider this following reaction, write the rate law for the reaction assuming it is a single elementary reaction. So again, my rate is going to be equal to the rate constant times concentration of nitrogen monoxide to the second power and then bromine to the first. Is a single step mechanism likely for this reaction? Well, what do we need for a reaction to occur? If you remember, for a reaction to occur, I have to have 1, molecules collide. 2, I have to have the collisions have to be in the correct orientation. And 4, those collisions have to have a certain amount of energy, meaning over the activation energy. Why did I say 4? It's 3. I can't count. Jeez. All right, so is it likely that the molecules will collide? Oh, yeah. Is it likely for these collisions to have the right correct orientation? We're talking about 3 molecules colliding in the right orientation. This is the part that is not likely for more than 2 molecules. Okay, so anytime I see a termolecular, 3 molecules in the reactants, it is not likely that it is a single elementary reaction. So the answer to B is no. It is not likely. that this is the appropriate mechanism for this reaction because of those three molecules having to collide with the right orientation. All right, so let's look at multi-step mechanisms. In multi-step process, one of the steps is going to be slower than the others. And this is the one that is going to hold up the reaction. It's going to be the rate determining. All right, and you can think of it as being, you know, the toll booths. Okay, Plaza 1 is slower. The backup appears at Plaza A. If Plaza B is the slower toll booth, the backup occurs at Plaza B. So the overall reaction can't go any faster than that slowest step. That is what is going to determine the rate. So if we look at this equation, nitrogen dioxide plus carbon monoxide yielding nitrogen monoxide and carbon dioxide, we find the rate law experimentally to be K times the concentration of nitrogen dioxide squared. Because this reactant does not appear in this rate law, we can assume that it is not an elementary reaction. It is important that carbon monoxide is present, but it does not affect the rate of the reaction. Okay. These things suggest that the reaction appears in more than one step. Proposed mechanism would be this, step 1, step 2. The intermediate, nitrogen trioxide, is consumed. I have a slow first step and a fast second step, so my rate is going to be determined by the first step. Doesn't appear in the CO doesn't appear in the rate law, and my rate then is K times the concentration of NO2 squared, because that is from this elementary equation. And that was experimentally what was determined, so it looks like this mechanism might describe how this reaction actually proceeds. Okay, so writing the equation for the overall reaction, this is the intermediate. I have 2 dinitrogen monoxides decomposing to 2 nitrogen molecules and an oxygen molecule. That's the overall equation. The rate law is dependent on the slow step, so the rate is equal to the constant times the concentration of dinitrogen monoxide. What happens? Oh, the rate law for this reaction is found to be this. Now this leads you to believe that that might be an elementary step. However, what is the molecularity of this equation? Well, it's termolecular, so that's unlikely. Okay. So the rate law suggests that there's a mechanism behind this. And here's the proposed mechanism. If you notice, that slow step now is the second step. Second step. What happens then is this intermediate gets backed up and it actually starts going the other way. So this fast step actually sets up what's known as an equilibrium, with reactants forming the products and the product going back and forming the reactants for that first step. So that includes forward and reverse reactions. Well, what do we do with that with the rate law? Well, first we look at the overall slow step, and the rate law for that would be this. Remember, all the steps in a mechanism are assumed to be elementary. Now this, this includes an intermediate. We don't typically have intermediate in rate laws, so how do we find the concentration of this? Well, it can form 2 ways, with nitrogen monoxide to form it or by decomposition to form the others. So the reactants and the products of the first step are in equilibrium. The rate forward is equal to the rate in reverse. Well, what's the rate of the forward reaction? K times NO times Br2. Backwards is NOBr2. Can I solve this equation for this intermediate? Yes, I can. Can I then sub that back into that first rate law equation that contained this? Yes, I can. Okay. All of the rate constants for those equations get bundled up into one, and I end up with this rate law that's the first one I came to. So here will be an example that we'll do in class. You try it on your own first, and then we'll go over it in class. Okay, to finish out the required content for the kinetics unit, we're going to talk about activation energy and specifically the Arrhenius equation and how those two relate. It's going to be fairly quick. So, if we look at the Maxwell-Boltzmann distributions, the fraction of the molecules can be found through the expression F, known as a frequency factor, is equal to the natural, well, E, to the negative to the activation energy over RT. R is the gas constant, and when we say the gas constant, we mean the one that is in joules. It's 8.314 joules per mole Kelvin. And is it joules or kilojoules? Per mole Kelvin. T is in Kelvin, obviously, and we can, what can we do with that equation? Well, Arrhenius developed a mathematical relationship between the rate constant and the activation energy. He put in this constant A, which is a frequency factor. And that's a number that represents the likelihood that collisions would occur with the proper orientation. So this takes into account the orientation of the collisions. The activation energy obviously takes account for the proper energy available when those molecules to collide for the reaction to happen. And we can relate that to the rate constant for a reaction. How do we actually use this? Well, we can take the natural logarithm of both sides, and if you do that, you get the natural log of K is equal to negative EA over R, activation energy over the gas constant in joules per mole Kelvin, times 1 over the temperature, and the natural log of that frequency factor. Remember, T has to be in Kelvin. And if you look, hopefully you notice that this is the same format as the equation for a straight line. Y is equal to mx plus b. The slope is going to be activation energy over R, negative. So if we plot the natural log of the rate constant and versus the 1 over Kelvin in the temperature, we can get a straight line, and then we can calculate the activation energy. We'll be doing a couple of examples using that in class.